So the Kalman filter was really designed for dynamic systems, but actually it resembles an already existing optimal linear predictor for static system. So if you have a linear stochastic static system, so there's no dynamics, but you want to estimate something at a certain time, or you want to estimate an unknown parameter. Also, in this case, you can come up with a dynamic stochastic state equation, as you see here. So some unknown state Z, which could be maybe, for instance, be hydraulic conductivity at multiple nodes, or infiltration capacity everywhere, or on a grid, or the groundwater level, or at a certain time, or well, also the long-term average groundwater level maybe, or soil moisture content. That depends on some model. So it can be any model that maps things that you do know, that you observe, to like rainfall, or I don't know, or maybe some terrain properties to estimate that static state. And you also have a system noise or model error. And then at a number of locations, maybe you can have actual observations of that state, or something that is observations that are related to that state with some measurement error as well. And then again, these are again the statistics. We assume that the vector of system noise is has a 0 expected value, and the covariance is known. We also have that the measurement error is mean 0, and the covariance of the measurement error is known, and of course the measurement error and the model error are assumed to be independent. So this linear stochastic system can then be employed to get something that resembles the Kalman filter equations, but there's no time update, and there's no time update, separate time update and measurement update here, but we have a optimal prediction right away, which is based on the model prediction, a priori prediction, plus a Kalman gain matrix, which is equal to the observations minus h, which is the measurement matrix, times the model prediction. And this looks like the equation for P. Also in the Kalman filter, instead of having M here, we have Q directly. The same for the Kalman gain. We have, instead of M, we have Q. Yeah. So this is the weighting matrix that depends on the relative magnitude of Q and R and the measurement scheme H. So with that, we have an optimal linear predictor. Yeah. That predictor is unbiased. It means that the expected value of the optimal linear predictor is equal to the expected value of Z itself, which is equal to our model prediction, a priori model prediction. We have a minimum, this variance, you can show that among all the linear predictors, this one, the one that if we calculate Z like this, it has a minimum variance. So the trace, which is the sum of the diagonal elements of this one, is minimal. Yeah. This is a so-called best linear unbiased predictor, therefore. We also call it Bayesian. That's the same as the Kalman filter. They actually all make use of Bayes' rule. So you have some a priori estimate, and then with information of given the measurement of the probability of the measurement given a certain state, we can also calculate the optimal prediction given the measurements. So we have in Bayesian terms, we also often talk about an a priori estimate, which is in this case the model estimate, and a posteriori, where we have an optimal prediction and a prediction error covariance matrix, where we know that the magnitude of P is always smaller or equal than the a priori uncertainty. So we're always reducing uncertainty by adding observations. Now let's apply this static linear predictor to an example that we showed before, where this is the Tarawara catchment, where they used a TDR observation device mounted on a small tractor or whatever it is that can be pushed into the ground, and they took about 2,000 samples to map out soil moisture. Yeah? So what we're going to do is we know soil moisture at 2,000 locations, so we have a very pretty good field of the soil moisture at a given time step. And let's assume that we do not have 2,000 observations, but we only have 100 or 103 of those. So we take a subsample. So what we do have is auxiliary information. And this is the so-called Tarawara catch. This is the so-called digital elevation model of the Tarawara catchment. This shows you the elevation with respect to sea level. And you can see that this is the outflow point of the catchment. And what we can also use, what we also have is 103 locations where we have soil moisture observed and this is soil moisture observed in percent. Yeah. So what we're going to do is we're going to first create a model that predicts what the soil moisture is going to be everywhere, and then we're going to update that model with these observations using the static linear predictor. So this is the auxiliary information that we're going to use. For those who did follow the course on land surface hydrology, they must have heard about top model, which is one of the most well-known models in catchment hydrology, and they relate actually the total accumulated flow to what is called the topographic index. The topographic index is the logarithm of the upstream area divided by the tangents of the slope for every cell. So for every cell you see what its upstream area is by creating a drainage direction map. And of course, cells that have a large upstream area and a very small slope have a very large value of the topographic index. And that means that they receive a lot of water from above, but they don't have the capacity due to the small slope to get rid of the water. So they are likely to be wetter than the ones of the lower values of the topographic index. Yeah. So especially the red and yellow, you can see the red, orange, and yellow parts are the ones that probably have the highest soil moisture. Now, if we do a regression between this map of topographic index and our 110 observations, so we have 100 or we have 103. What is it? 103 observations where we have soil moisture and topographic index, and we make a scatter plot of that. You can see there is a mild relationship. If the topographic index becomes larger, soil moisture content becomes larger as well. And what we do is we fit a regression equation to it, stating that soil moisture is equal to 2.73 times the topographic index plus 6.5, which has a correlation coefficient, explained variance of close to 30%. Seems to be not that high, but it's effective, as we will see later, especially if we do an update with observations. We can get what I did is I calculated the residuals between each observation and the model, the line, and then also calculated the variogram of those residuals, and fitted a spherical variogram with a nugget of 0, a range of 105, and a sill of 9. Yeah? So the variance of the residuals, of 15. The variance of the residuals is equal to 15, and this is percent squared. It's a weird unit, but it's a variance of something which is a percentage. We also assume that the standard error when measuring soil moisture with the TDR is about 3%, which is a little bit on the high side. Usually it's close to 1%, but that's when the TDR is fixed in the ground, and now you basically insert it. So we were a bit conservative in terms of the accuracy of the observations. So now let's set up the state equation first. So so we have n locations, a couple of thousand points on a grid. And for every location, we apply this regression equation. That's our model. So we have the topographic index map that gives me the topographic index at n locations. And of course, we also have this intercept here. So we also have, this is the U matrix, and this is the A matrix, and this is the vector of noises. And the U matrix, or the U vector, sorry, as a 1, and then all the topographic indices there. And then we just have the parameters of the regression equation here. Yeah. We also have the measurement equation. That's this one. That is the TDR moisture content at a certain location as 1. If theta 2 is observed, then we get a 1 here. Yeah. And so on. And of course, we have the observation locations of the observation errors there. Okay. So this is the state equation, which is a static equation, the static stochastic state equation, and we have an observation location. And then we apply the Kalman filter with this, yes. So from this we can calculate R. We assume R to be we assume the matrix R to be a diagonal with the variances which is equal to 9 on the diagonal and zeros everywhere, and the matrix Q can be calculated because we assume this to be a wide-sense stationary random function, the noise. So if we have the variance and we have the range, and we know it's a spherical semi-variogram, we can calculate the semi-variance between any of those, and the variance minus the semi-variance is the covariance. So we can completely fill the covariance matrix Q. So so I've done that, and then let's see what happens. So if we just only use this part here, yeah, this is only so that's the model prediction, yeah. So we take the map of topographic index, we apply this regression equation, which is nothing more than evaluating this part of the state equation here, the deterministic part of the linear stochastic system, a static system. We end up with this. This is the a priori prediction with the regression model based on the topographic index of the moisture content. There are some weird things here because on the edges the topographic index does strange things, but you can see of course the location where when there's discharge the main channel is also there, and those are the wettest location. And then we include the 103 observations and do the update. Yeah, so we basically evaluate this set of equations. Yeah, so we calculate from Q and R and H that we have, we calculate the Kalman gain, and then this is the model, this is the a priori that we had, and then we correct it by this term here. So if we do that, this is the a priori prediction, we get the a posteriori prediction. So this is the a posteriori prediction after updating with 103 TDR observations. And of course we also have P, which is the covariance of the prediction error. If we take the diagonal of that, which are the prediction error variances at each location, we can make a map of that, and you can see that of course the prediction error variances are going to be large at the edges where there's no observations, but you can clearly see that where the observations are taken, we have much lower errors, and even errors that are lower than the observations, because we're using both the model and the observations, so the resulting error variance is smaller than either of the two sources. Now, is this any good? Now, in this case, we also have the map based on 2000 TDR data. So if we look at our prediction fields after updating with the static linear predictor and say the almost exhaustively sampled field, you see that we're doing a pretty good job. So that is actually show the power of the static linear predictor, which is a very simple way of applying a Kalman filter type of predictor for a static property like soil moisture at a given time. So for the last example, we're going to move back to the groundwater and we're going to talk about network optimization. So this is our groundwater flow equation, but now we're going to 2 dimensions. Yes. So this is a 2-dimensional groundwater flow equation. So this is the transmissivity, this is the storage coefficient, and we have flow in X and Y direction, and we also have some, this can be a pumping term, but this also can be recharge, for instance. This is the forcing term. Now, if we discretize this one, we get a finite difference approximation. We can write it as a dynamic linear stochastic state equation again. We add system noise because we have errors in T, we may have errors in the storage coefficient, we also have errors in the forcing and in the boundary conditions, and all these errors are taken together in this added noise. Yeah? They represent all the errors accruing from those sources. We have a measurement equation. We measure at certain times, at certain places, we measure parts of the observations. And H is actually a monitoring strategy. It determines when and where we measure, right? This can actually change every time. So the matrix H can change. I told you, for instance, suppose that we remove one of the piezometers, then, you know, this one loses a row or a certain time step. There is no, or at a certain time step, an observation is not being taken, a 1 can be turned into a 0. So this is our monitoring strategy. It determines where and when we observe. Now, can we then optimize that or use that monitoring strategy to make sure that the errors of our time update, the final prediction errors of our time update are small enough so that we achieve a certain accuracy. Now, if we look at usually it's interesting to look at the diagonal of P, which is the variance Pxx. So that's the diagonal of the covariance matrix of the time update. And if we map that as in space for different time steps, you can see it's a function of space and time. For instance, this is a very simple model with fixed boundary conditions and recharge. And this is the value of P at the diagonal. And you can see we have one observation in the middle. Yeah. So this is just after an observation, just after the time update has taken place. Now, after, if we don't observe anymore, then after some time, this is what it would look like. Yeah. So you see that it grows in time. This is just after an update, and then just after an update, and then it grows in time. So can we use that to strategically place our observations in space and time to make sure that this thing doesn't grow higher? So that this thing doesn't get so high that maybe, for instance, it remains below 4. How many times do we have to observe? Or maybe we can observe not so much in time, but more at 2 locations, for instance. So that's the optimization that we want to work with. And the nice thing about the Kalman filter is that if you assume that your system dynamics are not changing in time, so that's usually the case, with a ground, if you have a strictly linear groundwater problem, that's actually if you are looking at groundwater flow in confined aquifers. Then the system dynamics are the value. All the values of A are not changing in time. Yeah. And Q, you assume Q and R also to be constant in time. Then the only thing you're changing is the monitoring design, H as a function of T. Yeah? And you can see that because Q, A, and R are constant, to calculate the prediction error covariance matrices, M and P, you don't need the actual value of the state. You don't need to know what the actual value of the observations are going to be. The only thing you need to know is where and when you observe. So you can use this property to optimize the monitoring strategy such that P, or the diagonal of P, is smaller or equal than a certain threshold value, and then optimize taking observations in space and time. So that's quite powerful. You don't have to actually observe, but before you observe, if you know what the error statistics are, you know what the system dynamics are, you can do optimization. So just as an example, this is a simple 30 by 30 node groundwater flow system. We have a fixed recharge. We have fixed boundaries on the side. Yeah. And we have, of course, some noise on it. So we do probably have some errors in the boundary conditions and in the recharge. And we observe at 16 locations. Yeah. We have a system matrix with an alpha that is equal to 1. Yeah, we already saw in the previous example what the system matrix looks like in a groundwater example. And then what I map here is the ratio of the variance, the average value of the, basically the average of the diagonal components of the P matrix, which is the average prediction error variance across the field, divided by the a priori covariance. This is at a measurement time, exactly at a measurement time. And you can see where we measure, these variances are going to be close to 0, not exactly 0, because we do have a measurement error. And this is between measurement times. So if we haven't observed in a couple of time steps, and then you can see that the error grows, and of course it grows largest in the middle. And the reason, of course, is that we have more or less fixed boundary conditions. Yeah, we have fixed boundary conditions here. So we know what the head is going to be on the side, even though there's some error attached to it. There's always a model error. And here the groundwater table is free to move, so the error is also larger. Now let's see what happens if we look at in time. If we look at an observation node and we look at the grid node in between observations. Again, we plot the ratio of the prediction error variance of the time of the measurement update divided by the a priori model error, and we can see that it grows, of course, higher in between observations than at an observation location. Yeah. And then after updating, even though you don't measure in between the observation, you can see you can reduce, just because of the system dynamics and also the spatial, possible spatial correlation in the system noise. You can also reduce the error at locations where you don't observe. So with this in mind, we can then also try to optimize and see what the effect is of measuring more in time or measuring more in space. And this is a figure from this book that I'm co-authored together with some source statisticians on sampling for natural resource monitoring. And this is a example of a Kalman filter where this is the ratio of this is the spacing between observations. Sorry, this is the spacing between observation, and this is the observation frequency. And this is the discretization in time, and this is the discretization in space. So it's normalized with that, showing you that for different, and these are lines of equal ratio of variance of P divided by the variance of Q. So here, in this domain, we are getting more and more accurate because we're measuring more in space, or we're measuring more frequently in time. And you can see that measuring in space and measuring in time are interchangeable, because these are lines of equal variance reduction. And we can get the same result by either measuring more in time with higher frequency, or measuring less in time and then using more observations. And this is a figure that you can use if you know what your system properties are, you know what your discretization is in your groundwater model. You can actually optimize, use this already to find an optimal sampling scheme in space and time. Okay, so the last 50 minutes, this lecture is called State Estimation and Data Assimilation. So we didn't talk much about data assimilation yet. Well, state estimation is where you have a state equation and you estimate either a static or dynamic state in time using observations and optimally combining state predictions or time updates with measurement updates into a measurement update by ingesting the observations through the linear Kalman filter. And this is actually one particular case of what we call data assimilation, which is a much wider range of research than the Kalman filter or state estimation itself. What is data assimilation? Well, it's actually in an optimal, that means in a probabilistic sense. So optimizing some probabilistic norm that could be the covariance or variance of the prediction error, but it could also be maximizing the probability density of the conditional probability density of the prediction by combining predictions of dynamic models and observations. And these observations do not have to be point observations or in situ observations of output variables, but these could also be of parameters. It could be integrated observations. For instance, we can use runoff to optimize catchment soil moisture, for instance, because we know that if the runoff is higher, the discharge, for instance, that the catchment is higher, probably the catchment is wetter as well, so we can use that. But we also can use, for instance, remote sensing data. Now, what are the advantages of data assimilation? So combining mechanistic models with observations above purely statistical models. Well, first of all, they yield physically consistent estimates in space and time. Yeah? If you just interpolate between observations and geostatistics at different times, and you have observation, you have these interpolated surfaces of groundwater levels, for instance, or groundwater heads, it doesn't, given the observations of, it doesn't ensure that your water balance is being respected. Whereas if you use a groundwater flow model and you ingest data by a Kalman filter or any other data assimilation technique into the groundwater flow model, the model dynamics makes that you have physically consistent estimates. It means that they are physically consistent in space and time, and they are at least closely adhering to some conservation principles, for instance, the conservation of momentum or mass or even energy. You can use them for point models, so for instance, an infiltration equation at a point, but also for partial differential equations. You can use a plethora of different types of observations, as I showed you. And you often compare to especially stochastic space-time modeling, and I've done that myself in a couple of publications. If you really want to do purely statistical space-time modeling, often you see that because of the time dynamics, these models cannot be assumed. These statistical models cannot be assumed to follow from, for instance, stationary random functions. They're often non-stationary random functions, and it becomes quickly complicated because you have to include a trend that then has to be estimated and so on. The disadvantage of data assimilation methods is that they're quite computationally demanding. So what I'm going to show you is actually a very general framework of data assimilation, what it does. It's a little bit mathematical, but it gives you a good overview of what data assimilation does. Data assimilation, in general, we have a so-called state equation. So we have z as a function of k. Time step k is some function of z of a previous time step, some forcing, and a parameter, plus noise. By the way, this noise can also be, this is additive, but it doesn't have to be additive. It can also be part of the function itself. Now, this is written differently as the linear state equation, so this can be any nonlinear function. It can also be the solution to a partial differential equation, right? And then we have an observational equation. So we have an observation operator that maps the observations, the state onto the observation space, and some additive noise. So this can be a nonlinear function or a matrix function, even nonlinear matrix function of the state. So now you see the difference is that nothing is necessarily linear. And what we typically do with data assimilation is solve this minimization problem. So we try to find the optimal estimates of zk to z1, so a whole set of states in time, such that we minimize this criterion. Now, what does it look like? This is the difference between the observations and the model predictions. We want to minimize that, and that's weighted by the covariance matrix of the model error. We do want to minimize the errors in the model, so we want to minimize this thing as well. And there is this weird thing here. Yeah? Remember that in Kriging, we wanted to make sure that in ordinary Kriging that the prediction was unbiased, and we used an additional variable for that called the Lagrange multiplier. Well, this is a little bit similar. What we say here is that the model plus the noise needs to be equal to the state. Seems to be gratuitous because that's what we assume. But of course, if we want to have a solution that's physically consistent, so we want to make sure that the final states obey our system dynamics. And therefore we add this term. This is the unity matrix, and or this is unity vector, for instance. Sorry, and this is called this is a vector of Lagrange multipliers, and it's actually called the adjoint state. That is what the name is. It's adjoint state. So what the Kalman filter does, if this is linear, is actually minimizing this thing. But then this one is linear, and this is linear as well. That's what the Kalman filter does. So it's a special case of this. Now, it may well be that the initial conditions are not exactly known. So we also want to include uncertainty about Z naught. So we get an additional term in our optimization criteria that makes sure that our initial estimates that we have, that's this Z wave here, is as close as possible to the true one. And that's, so we need to also have the so-called, this is the covariance matrix of the error in the initial conditions. It may also be that the parameters are unknown. We do not know the parameters. So if the parameter is also unknown, we get an additional term here in our optimization criterion that minimizes our a priori estimate of the parameters with the unknown parameters. And actually, if we minimize this whole shebang, then we're not only getting the optimal adjoint state or optimal state, ZK, but we also get for free an optimal estimate of the parameters. So we can use data assimilation to do two things in one go. We can optimize the state at every time step, and we can also calibrate our model while doing that. So we get optimized estimates of the parameters. Yeah. So this, now the trick then is, how do we minimize this whole criterion? And there are different types of data assimilation methods, so-called recursive methods, and or filtering, and there are batch methods. That do that. There are also methods that directly try to optimize this. Now, what you see here is a sort of a family tree of data assimilation methods. There are other different data assimilation methods that we can use, but these are sort of the methods that we see in the literature. We get this so-called heuristic non-optimal methods. They basically don't care at all about these minimizing this set of equations, so they don't take that into account. They are very simple methods where we either directly insert the observations into the state, or we do a simple correction where we do on a element by element base, we correct the state by a weighted average of the observation and the state, very much like we showed in our simple example of having two types of predictions. And there's so-called Newtonian nudging. That is a way to where you basically add to your stochastic system, you add some additional inputs that you try to nudge, change the value of recursively, such that your model comes as closely as possible to your observations. That's called nudging. So these are all heuristic methods. And then you have these optimal methods, and they yield approximately the best unbiased predictors, or minimize, actually, to some degree, either the first three, or the first four, or the first five, or subsets of that criterion. There's filtering, and those are so-called recursive methods. So that means you do a prediction, you get your observations at a given time, and then you insert the observations in one go, or at that specific time, and that is used then as initial condition for these optimized state. Prediction is used as initial condition for the next time update. Well, if the system is linear, you have a Kalman filter. There are all kinds of approximations for nonlinear models. There's the extended Kalman filter, which came about, which is problematic if your errors are large and your time steps are large. It doesn't work anymore. This is actually linearizing you linearize the nonlinear equations and then basically apply the Kalman filter. Yes, the ensemble Kalman filter and the particle filter, these are very popular these days, and they are standard issue of data assimilation methods. There are R and Python codes for that you can use. They're often used a lot. They basically use a Monte Carlo type of simulation to approximate the outputs to get around the nonlinearity of the model. And then there are smoothing methods. What smoothing methods do actually is they take all the observations into account in one go. And then smoothing can be, so they take all the observations of Z0, of Z1 to ZK in one go, and then try to minimize that criterion. That can again be done recursively. So we basically go from, there are smoothing methods that go from Z0 to ZK, and then maybe, and then they iterate a number of times, or they go back from ZK to Z0 to ingest all the observations. So they are still recursive. They look like the Kalman filter, but they take all the observations in time into account in one go. That's so-called Kalman smoother is one for. But more popular is finding an optimization algorithm. But then you need an adjoint state. You need to find, you have to have a model that describes this lambda case. You need an additional model, dynamic model, to calculate this dynamic, the dynamic evolution of this adjoint state lambda. And making an adjoint model is a lot of work. It's quite complicated. And you do that once, and you do that typically if you don't want to change much. If the model is not changing much in time. And then you use so-called variational data assimilation. You basically do a dynamic optimization of this using variational methods and a dynamic model of lambda. And that is often used in numerical weather prediction modeling. So where they apply data assimilation to estimate, for instance, they do a forecast with a numerical weather prediction system, and then they use observations of near surface temperature from satellite, but also from in situ observations, but also observations from weather balloons or from large meteorological towers, and all that information is ingested into the system by so-called variational data assimilation to get an updated weather state. So all the pressures and temperatures and relative humidities, but also the state of the land surface are updated, and that gives you a better initial condition for the near forecast. And that's very effective because the atmospheric system is quite chaotic, so it depends very much on how accurate you know your initial conditions. So if your initial conditions are improved, you're going to do much better. And especially the European Center of Medium Range Weather Forecasting are quite famous for their data assimilation system. And reanalysis data like ERA 5 is based on that variational data assimilation. Now, filtering is actually much better suited for forecasting. So if you have a linear state and you do forecasting, extrapolation, you will use a Kalman filtering. If you have a nonlinear state and you do forecasting, typically you use an extended Kalman filter or an ensemble Kalman filter or a particle filter. If you want to do also data assimilation, if you also want to do, you want to ingest all the observations in one go, and you also want to do parameter optimization, then either a Kalman smoother or a variational data assimilation is the way to go. Yeah. So smoothing is also is more for interpolation. So you also use observations from the future to optimize this state. Yeah. Like I said, you can have a recurrent algorithm. You basically go through the state like this, and then you go back, or you go through it a number of times. That's one way of doing it. That's a Kalman smoother. Or you minimize that set of equations that I showed you, and then you minimize in one go by estimating the value at all the locations in one go. Now let's show you a little bit an example of data assimilation and remote sensing, how this is really worked. Typically you would have a hydrological model that, for instance, estimates what the soil moisture is at a certain time, and then that soil moisture would then be used as initial value for the next time step. And there, and you go and go and go, you progress in time. Yeah. Of course, if you make an error here, that error will accumulate in time, right? And the error grows larger and larger into a certain value. If also soil moisture is observed from space, for instance, there are radar, passive and active radar or microwave systems that can measure soil moisture from space, maybe we can use this to update the state. Well, what they typically do then is they have a so-called radiation and emission model that simulates what a satellite would observe if this would be the real state. Yeah. So they basically mimic the observation system of a satellite. So you get a simulated satellite observation that is related to the state, of course with some observation error as well. Now, and these two are then compared to calculate a Kalman gain or any optimal weighting to get an updated state. And this can be done recursively with a Kalman filter, or probably is non-linear, because this one is non-linear and the model is non-linear. So you probably use an ensemble or a particle filter, or ensemble, usually ensemble Kalman filter, and then it's used to improve. You have a better initial state of your model, and therefore your forecasts are going to be better also because your initial conditions are going to be better. Yeah? So this is a data assimilation and remote sensing. Of course, you can also include in situ observations if you want to, not only, so different kinds of observations can be used. Now, this is an example where this is done. In this case, you do it recursively, but you can also take all the satellite images from T0 to TK and then ingest them in one go. Every time step you redo that, taking all the observations available to get the best optimal estimate of all time steps, given all the observations available, by minimizing these criteria I showed you. And this is an example of a group at MIT from 20 years back already, where they have a true moisture state that develops in time. They have a model that tries to estimate it, and you can see there's errors, but they also have satellite images. This is a very high footprint, and this is a smaller, this is a high resolution footprint, and this is a low resolution footprint. But you can see that even if you have low resolution data, and you ingest them, you get much better estimates of the state, of the actual state, than the model only. Yeah. So you actually effectively downscale here using the model. You downscale by data assimilation. You downscale the observations of the satellite to get improved estimates of the soil moisture at a higher resolution.